in all the previous lectures, we mainly assume that the quantum algorithm will be executed on the ideal quantum computer, and then there will be no error. So we can only discuss about the accuracy, the correctness of the quantum algorithm, but real hardware is not, unfortunately, as accurate as you are expecting. And then especially and the reason you are expecting the quantum algorithm will just work as you are expecting is because when we discuss about the classical computer, nobody really cares about the noise because um, there is very extremely little chance that during the calculation there will be actually noise error. However, and then all the most of the error were caused by the mistake of the programmers, not by the hardware. Unfortunately, quantum computer is complete opposite situation because if you think about the simplest quantum states such as this kind of qubit, then the most important information is not just a 0 or 1, but the important information is encoded inside this probability amplitude. And then this probability amplitude can have any value in the real in the complex number. So the if you are building your own quantum computer, then your task is to make sure that this value will be as accurate as possible. And then unfortunately, the current level of the accuracy is quite limited. So that's why it is called as noisy. And then intermediate scale means that um, um, if, if you imagine you want to solve the realistic hacking, or let's say that you want to use the quantum computer to hack the current cryptography system. Then I showed you that the Shor's algorithm, in principle, can break the something called as RSA protocol, which I will introduce in the next lecture. However, if you really think about how many qubits do we need to break the current RSA system, then you need at least a few thousand qubit, or more realistically, you will need hundreds or tens or hundreds of thousand qubits. So, and then the largest number of the qubit you can expect is varies depending on what kind of physical platform people are using, but it will be order of a few tenths, or like 20 or 40, 50 or 60 or something like that. So the current number of qubits, current available number of qubits is really small compared to the ideal situation. So that's why it is also called as intermediate scale. So you will frequently hear the acronym like noisy intermediate scale quantum, or more simply NISQ era. And then that means that we are living in the NISQ era because we are expecting that the noise or error in the quantum computer will be reduced as people are developing further, and then we are expecting that we can increase the number of the qubit, but but to overcome such kind of limitation, it will take a while. Yeah, I don't know. Yeah, it can be 5 years, 10 years, or more likely 20 years. So it is not easy to tell when we can reach such kind of level. So this year, this era will last for a while. Yeah, so so now we should be somehow realistic, and then we should develop more metric to evaluate the current situation. So And then today I will actually introduce how we can avoid or overcome the problem of the noise part. But before I discuss that part, let me also introduce the concept of the quantum volume, because people wanted to compare different technology for the quantum computing. So they need some kind of single metric to compare or represent the current situation. So because you are familiar with the concept of the with the classical computer, you are generally familiar with when with the quantum with the classical computer. How do you compare the performance of the different computers? You generally consider what is the bit of your CPU, or what is the clock speed of your computer. But if I say that what kind of computer you choose, if I give you two options like a 64-bit processor, but its clock speed is order of like 100 megahertz only, while another CPU is only 8-bit, but clock speed is 1 gigahertz or few gigahertz. Then which will be your choice? Well, that's not easy to determine. So that's why, and then a similar situation also applies to the quantum computer. If I say that which type of the quantum computer you would use, if I give two options like 10 qubit with error rate less than 1%, or order of 50 qubit, but with the error rate of the 10%, then which will be your choice? Well, I guess it's not easy to choose. So that's why we have to consider the concept of the volume, not just a single number. Well, volume is still single number, but what I'm saying is that we cannot just consider compare two types of quantum computer in the one-dimensional scale. So here this is from IBM, and then so IBM proposed a concept of the quantum volume for the first time, and then here this axis represent the number of qubits. So we might increase the number of qubit from 5, 15, 50, or 500, and then the error rate might be reduced from 1% or 0.1% or 0.01% or something like that. Then if you have this machine or this machine, then which one will be better? And then according to this calculation, they are actually equivalent. There is no improvement. So if your accuracy or the error rate is limited, then there is no point in simply increasing the number of the qubit. So this will also shows you that we have to work on the improving the accuracy in addition to the number of the qubits. So for example here, even if from here to here there is no improvement in terms of the number of qubit, yes, the same 100 qubit. However, if you improve the error rate or reduce the error rate, then there will be significant improvement in terms of the quantum volume. So that probably makes sense. And then another factor which is not represented here when you are considering the concept of the quantum volume is that not only the error rate or the number of qubits, but connectivity between qubits are also important. When I was drawing the quantum circuit like this one, I generally say that this first qubit can be combined with any of the different number of qubits. However, that's not always possible. So depending on what kind of physical system you are using, sometimes if you have the array of the qubit like this one, so it is like a lattice shape, and then there will be only the there the direct quantum operation between the qubit can be only limited by represented by these lines. And then if you want to do any quantum operation between this qubit and this qubit, what you should do is apply a repeat the swap operation between this one and maybe this one and this one. Yeah, so yeah, to implement well, yeah, not yeah, probably you don't need the last swap operation, because once you move the quantum information stored here to here, then you can directly do some kind of quantum operation. However, what the point is, yeah, if you have this kind of the limited connectivity, then the quantum the performance of the quantum computing will be limited. So yeah, connectivity is another factor you should never forget when you are estimating the quantum volume. So and then um, here, this is another chart which shows how good is the quantum computer compared to the classical computer or supercomputer. So yeah, this one shows that if our number of qubit is limited down to here, then the however small the error rate is, that there is such kind of quantum the computational power of such kind of quantum computer is still comparable to the classical computer. So to overcome the performance or the power of the classical computer, yeah, classical supercomputer, then we have to cross these boundaries. And there are two options we can cross the boundary. One is um, if our error rate is low enough, then just by increasing the number between somewhere like tens of qubits, then yeah, we can reach the area which cannot be simulated by the classical computer. Or another option is if you have some limited error rate, then you have to increase order of 10,000 or whatever, depending on your error rate. So yeah, there are different strategy to overcome the classical computers performance, but the final goal will be probably somewhere around here. And then here you can see that something called as the quantum error correction, or the error corrected quantum computing. Yeah, so yeah, today's topic is basically about the quantum error correction. Before we will continue the discussion about the quantum error correction, let me first start with the review of the classical error correction. And then let me ask you one question. So why are you using digital compared to analog? Yeah, if you, yeah, I don't know whether you guys are old enough to see all those analog technology, but when I was young, yeah, all the electronics are basically based on the analog devices. And then yeah, one of the most um, popular example for the analog device is about the sound device or the amplifier. So, and then in that case, the the challenging part for the audio device is that if you have some signal, some sound signal, like yeah, changing like this one, then whether how can you deliver the recorded sound information to the receiver, and then yeah, reproduce this original signal. And then yeah, I don't know whether you heard the terminology hi-fi, and then hi-fi means the high fidelity, and then fidelity means that how close your reconstructed signal close to the is close to the original signal. And then the most challenging part here is the if what happens if you have some kind of additional noise like this one, and then how can you remove this kind of error? And that's the answer to this. Well, yeah, in the analog domain, yeah, there are still some kind of technology like frequency filtering, because in many of the case, the noise occurs at high frequency. So just filtering out the high frequency component, maybe you can reproduce regenerate the original signal like this one very closely, but that was not enough. So what people eventually started to use was to digitize the information, digitize this analog information, and then reproduce that information, and then deliver or transmit that information to the receiver, and then receiver reconstruct the original signal. And then why is digital uh, more is better compared to the analog signal? That's because even though you might not consider such kind of concept, but the concept in digital already has the concept of error correction. Because if you learned about the digital circuit, then the first thing you learn is that digital information 0 and the digital information 1 is represented by some separated voltage, like 0 volt for the zero information, and then 5 volt for the one information. And of course, yeah, nowadays the accuracy or the control of the voltage is the the capability in controlling the voltage is improved a lot. So nowadays, people are using much smaller voltage, like 3.3 volt or 2.5, or sometimes people are using 1.25 volt for the to represent zero, as represent one compared to 0 volt. But in the past, yeah, or if you learned about the TTL, yeah, which is a transistor logic, then the typical standard was 0 volt versus 5, and there was a reason. And even before the TTL level, then for the long distance communication, people are using something a standard like plus minus 15 volt. So yeah, people were concerned about making sure that there is no noise, and the reason is, even if you are sending some information like 4 volt around here, there is still some amount of noise during the transmission. So even if we have some amount of noise, if we decide our threshold for the one as this range, then even though we have some kind of noise, they will be ignored. And similarly, for the 0, if we set some kind of range for 0 volt, and then as long as the noise remains within this threshold, then they will be recognized as 0. And then that is exactly what we mean by the error correction. So even though we have some kind of noise, those noise will be rejected by the design of the digital concept. And then so that's why people are interested in digital communication. And then even in the with the digital communication, there will be still some amount of noise, because transmission of the digital data over a long distance will probably incur some of the finite error. So yeah, let me review some of the property or some of the concepts in the classical communication channel, and then the error model. In digital communication, the error model starts with this kind of concept. Yeah, so as a sender, we want to send some information at either 0 or 1, and then yeah, of course, we hope that 0 will always transmitted as 0, and then 1 will be always transmitted as a as a 1. The problem is there is always some finite amount of probability that the 0 will be turned into 1, and then 1 will be turned into 0. And then this is, of course, called as an error. And then there is a finite probability. And then if I call the probability that 0 will be flipped to 1, the probability as a p, and then there is no reason why the probability that 1 will be flipped to 0, it will be the same as a p. However, for the simple discussion purpose, we generally assume that the probability that the 1 will be flipped to 0 will be again p. And then Yeah, we call this type of channel as a binary symmetric channel. And then yeah, for the rest of the discussion, I will simply assume this kind of concept. And now, then what is the probability that zero will be transmitted as a zero, and then it will be one minus b. And similarly, one goes to one is the probability is then one minus p again. So, and then yeah, if I summarize and if I compare some of the situation, yeah, let me assume that we are using just the one bit for the information transmission. In that case, let's say that let me find out the number. Assume that number of error bit, and then the probability of such kind of situation happen. And so if I assume that yeah, during the transmission of the one bit, the number of error bit will be either 0 or 1. Yeah, so if we had error bit only, there is no error bit, then what is the probability that we won't have any error in the transmission, or zero number of error bit? Then it will be 1 minus b, because 1 minus b is the probability that 0 will go to 0 and 1 will go to 1. And then it is 1 minus p. And then the number of the error bit will be 1 is, of course, it will be p. And then in this case, what we actually want is that the 0, the correct transmission is what we desire. And then the wrong, if we have any non-zero error bit, then it is non-ideal. Ideal. Then, if we want to improve the situation, another option is that instead of transmitting 0 only, what happens if we transmit a 0 0 to transmit a 0 information, and then 1 1 to transmit the 1 information? Of course, what we hope is a 0 0 will be transmitted as a 0 0, and then 1 1 will be transmitted and as 1 1. However, there will be always some case that the first when even when I transmit a 0 0, there is some chance that the 0 0 will be turned into 1 0. And then the problem is, if if we receive the 1 0, then we don't know actually whether it came from the 1 1 or 0 0. But what we can be sure is that there was some error. So if I compare the advantage of the sending 0 0 or 1 1 to transmit the information of 0, yeah, so in this case, my goal is not to transmit a 0 0 by itself, but in terms of the information, I want to transmit 0 or 1. However, because we were concerned about the error probability, non-zero error probability, we intentionally send 0 0 to represent the 0, and then 1 1 to represent 1. Yeah, we are transmitting 1 1 to represent the information of 1. And then in this 2-bit encoding, yeah, so we call this kind of situation as an encoding. And then yeah, let me also make a table similar to the 1-bit case. So in this case, we know that so yeah, and yeah, then what is the probability that there is zero bit error during this transmission? And in this case, the first bit should be correctly transmitted, and then the second bit also should be properly transmitted. So the probability that there will be no error bit is 1 minus p squared. And then what is the probability that there might be only one bit flip? So in this case, we might consider that maybe the first bit might be flipped, and then the probability that the first bit will be flipped is p, and then second bit won't be flipped, so it is 1 minus p. However, there is also another case that the first bit is correctly transmitted while the second bit is flipped. So there is twice the two types of such kind of case. So we have to we have to multiply two. Then what about the um, 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 and then there is also another case that both of the bits are flipped. So this is worst case, because in that case, even if we transmitted 0, 0, both of the bits are flipped, and then they will be 1, 1, and then people will just believe that, oh, maybe we received the correct information. So there was no error, so we will just accept this one as 1. In this case, if you compared to 1, 1 case, if we received only 1, 0 or 0, 1, even though we cannot tell whether which information was transmitted, but we can be sure that there was some error. So we know that we should request resending the that information again. So yeah, so receiving 1, 0 is not as worse as receiving 1, 1, even though we initially started with 0, 0. And then what is the probability? That means that both of the bits will be flipped, so it should be p squared. And then yeah, in this case, we know that the first case is the best, and then the last case is the worst, and then the second case is yeah, that's not, yeah, we cannot recover the correct information, but at least we detected that there was some problem. And then in this case, somehow, yeah, and then let me just give you some concrete number. Yeah, so let's say that the probability of error is only 10%, and then in this case, we know that for the 1-bit case, we know that the correctly transmitted probability is 90%, while the incorrectly transmitted case is 10%, and then compared to this 1-bit case, we know that for the 2-bit case, the correctly transmitted probability is actually lower than the 1-bit, because it is only 81%, while for the completely incorrectly transmitted case is only 1%. Then what about this probability? It will be, yeah, if you plug in 0.1 to the p, then it is 0.1, and this is 0.9, so it is 0.09, and then multiply by 2. So it is 18%. So if you look at this number only, then you might say that, well, yeah, then um, the probability that the information will be correctly received is actually less than the 1-bit case. So you might consider that the 2-bit case, 2-bit transmission is worse than the 1-bit case. However, that's not true, because what is the worst case is even though we receive the wrong information, we don't know that we received the wrong information, and then we don't request any of the retransmission. So that is the worst case. And then for the 1-bit case, the probability that we incorrectly receive and we uh, yeah, even though we receive the wrong information, we don't know, and then we will just take it as a correct value, is the probability is 10%. While for this case, because for the second case, we actually know that we received the incorrect information. So there is a high chance that we will receive the correct, we will request the um, retransmission of the information, and then yeah, eventually we know that we will have a probability that we will receive the correct correct bit. So in this case, the worst case only happens with the 1% compared to the 10%. So using the 2-bit is already much better than the 1-bit case. However, the limitation of this case is that whenever there happens any error in transmission, then yeah, then we cannot actually correct the incorrect correct we cannot correct the wrong information. So to correct the to be able to correct the incorrect information is that sending 3 bits instead of 2 bits. So if we transmit 000 and if we can receive 000 or 111, then it is definitely true that we will be able to tell well, yeah, if we receive either 000 or 111, then we can uh, have a large confidence that we receive the correct value. While if we receive um, something like 100, then what will be your guess for the original information? Probably it will be 000 because it based on the majority voting, then there are more zero than one. So in this case, in principle, we can correct the information. Yeah, of course, there is some chance that we might incorrectly correct the information. But yeah, let me just calculate those probability. So for the 3-bit case, the number of error bit is can be either 0, 1, 2, or 3. And then for each of the case, the probability that for the 3-bit case, the probability that we won't have any error is the 1 minus is the 1 minus p cubed. While for the 1-bit flip, in this case, maybe the first bit might be flipped, so it is p times 1 minus p squared, or uh, the second bit, only the second bit might be flipped, or the third bit might be flipped. So there are 3 combinations or 3 chances that um, one bit will be flipped. So the probability that even though we did not receive the correct information, but we should be able to uh, correct to the right information. So these 2 cases are still acceptable, while for the 2-bit error case, that will happen because 2 of the bit will be randomly flipped, and then in this case, if the first 2 bits were flipped, then the probability that p squared 1 minus p. However, maybe the second bit might, for this calculation, I assume that only the third bit is not flipped, and then only the third bit is correct, and then the first 2 bits are flipped. But there will be also other cases like only the second bit is the correct, or only the first bit might be correct. So there are three combinations that we will have 2-bit flip. So the probability is like this one. And then finally, the probability that all 3 bits will be flipped is the q to the third, or p cubed. Yes. And then for these cases are the worst case. So in this case, if we still want to confirm that 3-bit encoding is still better than 1-bit encoding, then we have to compare the probability that for the 3-bit case, the probability that we will have the incorrect information is is smaller than the probability that we will have the incorrect information for the 1-bit. And then for the 1-bit case, the probability is p, while for the 3-bit case, we know that the probability that we will receive the incorrect information is the summation of these 2 probability. So it is something like 3p squared 1 minus p plus p cubed. And then we want to we want to figure out at what kind for what kind of probability we will still have lower error probability compared to the one bit case if we are using the 3-bit encoding. So that's the relation we want to solve. And then, of course, this can be easily turned into the um, um, yeah. So sorry. Let me yeah. So if I expand the left term, or if I expand this part, then it is 3 times p squared minus 3 times p cubed, but there is also plus p cubed, so that is 2 times p cubed. And then if we want to have if we want to figure out the range of p which will satisfy this relation, then we can move all the terms to the right, and then 2p cubed minus 3p squared plus p, and then this can be a vector like 2p um, minus p, and then p minus 1, something like this one. So, and then to find out the condition which will satisfy this inequality is that if we plot this kind of um, third order polynomial, then we know that the coefficient in terms of in front of the third order term is a positive value. So the shape of the this third order curve or third order polynomial will look like this one. And then if I plot that one, and then to plot that uh, to figure out the correct to draw the correct plot, then we have to figure out where does this polynomial crosses the value of 0, and then there will be either p equals 0 or p equals half or p equals 1. So yeah, there is this curve will cross these 3 points, and then the probably the most reasonable plot will be something like this one. So what is the condition that this equation will be satisfied? That's when the either p is between 0 and half, or larger than 1. But we know that p is the probability. So the correct requirement for the for this inequality to be valid is when the p is between 0 and half. And when you see this kind of result for the first time, you might say that the 3-bit encoding is better than one bit only when the error probability is less than half. And then if the error probability is larger than half, then you might say that the 3-bit encoding is not good. However, that's not really the case. Let me ask you a simple question like I have 2 channels, and then one of the channel has the probability of um, error probability is only 10%, while I have another channel number 2, and then its error probability is 99%. And which channel would you choose for your information transmission? Maybe many of you will choose the p equals 10%. However, I will actually choose the p equals 99%. Why? Because I know that when I send out 100 bit, I know that 10 bits will be flipped for this case. However, for this case, I know that 99 bit will be flipped, and that means that um, if I just at the receiver side, if I just add a NOT gate right after I receive the bit, then I will always receive the correct information 99 times out of 10, out of 100. So even though the error rate of 99% might look bad, but it is not the case. It actually corresponds because we know that it is guaranteed that the received value will be always flipped, and then only with the 1% of the chance that we will receive so only 1% of case there is uncertainty. So compared to this 10% uncertainty, 1% uncertainty is much better in terms of the error, in terms of the communication. So the point here is when we have probability larger than 50% or half, then that is actually equivalent to having a less error probability than the 50%. So when we are talking about the error probability during the in terms of the communication, 50% of error is the worst case because that corresponds to just flipping a coin rather than doing a communication. So don't be fooled by this kind of limitation. And then this the conclusion that as long as the error probability is between 0 and half, then this this inequality is still valid, means that 3-bit encoding is always better than 1-bit encoding. So that is the result we will use. And then in this case, I mentioned that to transmit the 0 information, we are using 3-bit information, and then these 3 bits are generally called as logical 0, while for this original information, and then so this even though we have 3 bits, the logical bit for this case is only 1 bit. However, because we are using 3 bits, so each of these 3 bits are called as a physical bit. So for the 3-bit encoding case, we are using 3 physical bit to transmit 1 logical bit. Similar for 111 case, the 3 there is we will use 3 physical bit, but the logical 1 will be only 1 bit of logical 1 will be transmitted. So as I mentioned, we are using the majority voting for transmitting multiple to transmit the information of 0 or 1. And then we use the multiple bit, and then these are called as logical 0 and logical 1. And then as I already calculate the probability comparison. Now let's discuss the quantum error correction compared to the classical error correction code. And then there is some very important difference between the quantum error correction and the classical error correction. First of all, I mentioned that instead of just sending either 0 or 1, I said that we will transmit 000 or 111 for to represent the transmitted data. However, we know that there is no cloning theorem. So the first question you might have is it really possible to do any kind of cloning for making such kind of 3-bit encoding? Another question might be that when I explained about the digital technology, I said that they are originally designed to be error. They are robust against the error. However, all those quantum states such as psi alpha 0 plus beta type, then we are concerned that alpha and beta are analog value. So can we actually correct any kind of error in the quantum information? And then that is when the because when the concept of the quantum computer was first proposed, many people believe that such kind of technology won't succeed because people already knew that the reason the digital technology succeeded compared to the analog technology was because digital technology can utilize the concept of the error correction. However, for the quantum information, because it looks like error correction doesn't seem to be possible because of this analog looking like a situation. So many people were pessimistic. However, the guy, do you know who um, first proposed the concept of the quantum error correction code correctly? That is Peter Shor. And do you remember what Peter Shor did before? His name also came in the appeared in the Shor's algorithm. So, yeah, even though many people were pessimistic, actually, Peter Shaw proved that error correction is also possible even with the quantum computer. So, the contribution of the Peter Shaw is really huge in the quantum computing. And then the last question you might also have is if you consider the case for the classical communication, we actually to decide which one is the correct information, we actually had to measure whether to make such something like a majority vote. What we had to do is measure each of the bit so that we should know whether it was 001 or 110 or whatever value. And then only when we figure out each of the each value of each bit, then we should be properly correct the received information. However, once we make any kind of measurement, that means that the superposed state will collapse to one of the value, and then eventually we will lose the information. So that is a concern many people had initially. And surprisingly, Peter showed that it is actually these problems are not really making the quantum computing impossible. And then yeah, he showed that there is a really well-defined concept for the quantum error correction. So to discuss the quantum error correction, we should first have some error model for the quantum system. And similar to the digital information, we will assume that all the quantum channel also has error model such as a bit flip model. And then in this case, if we send some bit through a channel, then this channel might flip the qubit value with the probability of p, and then that one actually corresponds to flipping the given quantum state with we apply the x operator to the given quantum state, and then and occasionally this X operator is sometimes called as bit flip operator. And then still, we want to use a 3-bit encoding, something like before. So if we remember what we did for the 3-bit encoding in the classical communication, we turned the 0 information to 000 and 111, and then similar to that situation, we might consider that we might if I'm given this kind of quantum state, I might want to create this kind of superposition state. And can we always convert this information to this one? And the answer is yes, with this simple circuit. So yeah, again, if we have 0 information here, then this CNAC gate and then another CNAC gate will flip both of the. If I have 0, then there will the other two qubit won't be flipped. So you will obtain exactly 000. While if your bit is 1, then these values will be flipped. And then even if the quantum state of this one is in superposition, still we will have the superposition of 0, 0, 0 and 1, 1, 1. So that might not be as bad as we were concerned initially. However, the most challenging part is how can we measure the quantum information? How can we detect if there is any error, and then if there is any error, which qubit we should correct, and then we should do that even without destroying the quantum information. So how can we do that? So we might have created this kind of 3-bit encoding, but the problem is during the computation, there might be some kind of error, happening here, and then there might be one of the bit will be flipped. Then how can we find out which which bit is flipped? Well, to figure out to discuss that one, yeah, let me give you a little bit easier example. So let's say that I have some kind of let's assume that we want to compare two quantum state, and then we know that they will be some kind of superposition of either 0, 0, beta 1, 1, or we have this kind of 0, 1 plus beta 1, 0 type of superposition. And my question is whether it is possible to distinguish these two types of quantum state without destroying the quantum state by itself. So yeah, without destroying the superposition by itself. And well, you might feel like this might be almost impossible to determine between these two cases, but there is without measuring any of the quantum state. But here without when I said without measuring means that without destroying this superposition. And here it is still possible. And then the reason is the first thing you have to notice is that these two states have different parity. You probably know that the concept of parity. So yeah, for example, parity means that the number of ones, and then whether the number of one is even number or odd number. And then in this case, the number of one is 0, while for this case, the number of one are 2. So both of the cases are even number. So we would call this one as an even parity. While for the second case, both of these states have only one of one. Yeah, so it is odd parity. So for this case, we can actually distinguish these two cases because what I can do is if I have two qubits, and then if I have this might be the first qubit, and then the second might be the second qubit. So if I start with either 0, 0 or 1, 1, and then if I have this kind of circuit like this, and if I start with the 0, then when we have 1, 1, then the output of this one will be 0. And then if both of them are 0, so the previous case was a 0, 0. And then if we have 1, 1 case, this will flip, but this will be flipped back. So it will be again 0. So for the even case, we will have the measurement of the third bit will be 0, while if we have only one of them is 0 and the other one is 1, yeah, so whether we have 0, 1 or 1, 0, 1, 0, still the output value of this qubit will be 1. So the measurement of this one will be 1 or something like this one. So in this case, we call this third qubit as a syndrome qubit. And then syndrome means that some kind of symptom or so by measuring this syndrome qubit, we can actually decide whether it's a, even parity or odd parity without destroying the quantum state by itself. So if we use this kind of idea or apply this kind of idea to this case, then we can actually detect whether it is which bit is flipped. Yeah. So let's say that I want to measure the So if I add two more syndromes like here, and then I start with 0 and 0 and something like this one. And then if I apply the SNU gate on this one, on the first syndrome, I apply the SNU gate between the first and second qubit, while for the second syndrome, I will apply the SNU gate from the first qubit and the third qubit. And we know that, let's say, and then we will measure the result at here for these two qubit. In this case, let's say that so I'm comparing three different qubit, and then each of the parity will detect whether these two qubits are the same or different, and then for the second syndrome will detect whether the first and the third qubits are the same or different. And then we know that, let's say that if I have a three qubit, but the comparison of these two are the same, but if the comparison of the third and the first and the third are different, then we know that the result of and then in and then in this case, if we have this kind of equality or yeah, difference result, then we know that probably the third qubit is flipped. So yeah, we will correct this qubit. While if I have a different case list, like if the first pairs are different, but the third pairs are the same, for the these two are different, but these are the same, then we will typically will conclude that this second qubit is flip. And then if we had both of the for these two are different and these two are different, in that case we might conclude that the first qubit is flipped. So if I apply that such kind of idea, then let's say that the first qubit is flipped. In this case, because only the and then in this case we would measure something like a 1 1, because only this CNAT will flip this 0 to 1, and then this CNAT will flip 0 to 1. So in this case, if this one is flipped, then we would have this kind of 1 1 result. Then what about the second case, that the second qubit is flipped? In this case, the first syndrome will be flipped to 1, but the second syndrome won't be flipped. So in this case, I will obtain some value like this one. And finally, if I have if the third qubit is flipped, then in this case the first and in this case the first syndrome won't be affected, while for the second syndrome, because this only the third qubit only works on the second syndrome, so it will be flipped into this one. So I can write down like a 0 1. And then if you see these result, then if the top one is flipped, then we would obtain the syndrome like a 1 1, which means and then if I consider this measured result as a binary number, then that corresponds to 3, and then this one corresponds to 2, and this one corresponds to 1. So if this value exactly this syndrome actually tells us which qubit is flipped. And then what we can do is, let's say that if I have if I measure the result is something like 1, 0, then because I know that the third qubit is flipped, so what I can do is apply only the X gate on the third qubit while we just leave the other qubits untouched. And then in this case, we can actually recover the original value by using this one. And then we can see that um, the superposition state, like here, where it will be 0, 0, 0 plus beta 1, 1, 1 will still remain when the after we correct it with the X gate at this point. Yeah, so yeah, again, yeah, by using the syndrome measurement, and then yeah, we can still keep the superposition state like this one after the correction. And then that's the idea behind the error correction, quantum error correction code. Then the next question you might have is, yeah, all of my previous explanation for this one somehow assume that either at least one of the bit will be completely flipped. But we also know that the error won't always guarantee to happen, but it will happen in some kind of continuous fashion and then probabilistically. So yeah, you might wonder whether the previous previous complete bit flip model still valid for the typical for the most general quantum error correct error model, and then the answer is still, yeah, it is valid, because the syndrome right after the syndrome measurement, it will be the superposition of no error and the error case. However, once the syndrome, yeah, before the measurement, yeah, it is the superposition. But once the error syndrome is measured, then the quantum state will collapse to only one of the case, and then the still, yeah, the previous model is valid. So let's say that yeah, among the three qubits, one of the first qubit might be flipping, but not always. But yeah, something like 0 will flip with a very small amount of probability, like epsilon, and then the rest of the case it might still remain as 0. While for the one case, yeah, because we are assuming the uh, binary symmetric channel. So in this case, we can say that the probability of the error of bit flipping for one state will be the same error probability of square root of epsilon with the 0, and then the other, and then still we have the probability that it will remain as the 1. So if we have this kind of error, and then the, yeah, let's say that by I have the state something like alpha, yeah, alpha 0, 0, 0 plus, oops, beta 1, 1, 1. Then, yeah, because of this probability, we might actually have superposition of epsilon, oops, epsilon 1 plus 1 minus epsilon 0 plus beta square root of epsilon 0 plus 1 minus square root of 1 minus epsilon, and then um, yeah, this will be 1. And I forgot to include that there is tensor product of 0 and 0, and then there will be also tensor product of 1 and 1. And then what I can do is rewrite this situation with the square root of epsilon and then it will be alpha 1 0 0. Yeah, I will skip. I will omit the notation for the tensor product, and then the second term will be beta, and it will be 0 1 1. So that's one possibility, but there is still another term which is 1 minus epsilon, and it is alpha and 0 0 0 plus beta 1 1 1 case. So this is the situation for the error when the error occurs, and then if I feed this kind of quantum state to the syndrome measurement circuit, then for the syndrome measurement, because we have only the first bit is flipped, and then we know that the syndrome once we um, make the syndrome measurement, then it will actually flip to the 1 1 case, while for this case, the syndrome qubit won't be flipped because there are no errors. So we will have something like this one. So up to this point, it might look like we have the superposition of the error case and non-error case. However, what we will do is actually measure the syndrome, and then measurement of the syndrome will collapse the entire superposition, and then for that case we will only measure the syndrome bits, syndrome qubit, not the data qubit or encoded qubit. So yeah, let's say that if we the measurement of the syndrome gave us something like a value of 1 1, then in that case the final quantum state will collapse to only this one. And then for this one, because we have this measurement, we know that we should correct the first qubit. But if we measured our measurement of the syndrome gave us the information of 0 0, then we know that we don't need to correct this value, and then this is already a good quantum state. So yeah, whichever happens, and then even if an error happens only partially or probabilistically, still our scheme for the error correction still works. In the digital logic, the only type of the error we have to concern is the bit flip error. However, in the with the quantum state, we know that the phase information is as important as the absolute value of the amplitude, because whether there will be a constructive interference or the destructive interference is mainly determined by the sign of the amplitude. And then more generalization of a sign is the phase. So whether there is a 180-degree phase difference or the 0-degree difference, the interference appears in complete different way. So now, and then of course during the operation, there is also a lot of probability, not a lot, but there is some finite amount of probability that the phase will be changed. So we have to be concerned about the phase change. And then the next question is, how can we detect the amount of phase? Yeah, I asked you and then show the such kind of question in the one of the previous lecture, and then the answer was basically change to different bases, like plus minus basis, like which is defined in this way. So these are 0 or 1 was generally called as the computational basis, while these bases I just defined as a plus and minus. And then even though if we measure everything in terms of the computational basis, generally we cannot measure the phase value. However, by switching the basis from the computational basis to the plus minus basis, then we should be able to detect the value of the phase. And then to do that, to implement the basis change can be achieved by applying the applying the Hadamard gate. So that's our strategy. So what we are going to do is we will first assume that there is ideal channel, but not completely ideal, but there is a channel which won't flip the bit information, but it will only it has only some finite probability to flip the phase, and then yeah. So this is our first assumption, and then in this case, the action of the this error is that it is equivalent to applying the Z gate to the given input state. And then of course this Z gate is not applied all the time, but with some finite probability P. And then in this case, we will also call this Z gate as a phase flip operator. And then what we are going to do is, because we want to detect whether if we started with the plus state, whether there will be any phase flip in front of the or relative phase for the between these 0 and 1. So if there is some phase change, like a 180-degree phase change, then this will become a minus, and then that one will corresponds to changing to the minus spaces rather than the plus spaces. So to detect to detect whether there is any such kind of flip or not, what we are going to do is, first we will create the 000 state or 111 state by going through this part. And then yeah, by going through this part, yeah, we will either generate a 000 or 111. But by going through the additional Hadamard gate, then all the state will be changed into either plus 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 or minus minus minus. And then there will be some kind of operation, and then there might be some error. And then at the end of the operation where the error, then if we convert back to the computational basis, then all these plus sign and all these plus or minus vectors will um, sorry yeah, yeah, all these plus or minus bases or vectors will be converted back to the 0 or 1. So and then that means that if there was some error, then this repetition code, which was originally started with the 000 or 111, will be turned into one of the bit will be flipped to 1, or one of the bit here will be flipped to 0. So and then we know that how we can detect such kind of error by using the parity check circuit, or in other words, by measuring the syndrome. Yeah, so that's how we can detect for the phase flip error. Of course, there will be no ideal channels like only a channel with only the bit flip error, but there will be in general channel, or in general situation, there is also um, uh, um, with the same qubit, there can be either phase flip or bit flip. So yeah, in principle, we should be able to detect both of the both types of error. And how can we do that? And then the answer for that one is by cascading two types of the encoding in series. So what we can do is because we want to detect the phase flip, we will first convert the zero state to the plus 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 or minus minus minus. But we know that in each of these, the bit might be flipped. So to detect such kind of bit flipping, we will replace each of these plus state with another repetition code to detect the bit flip error. And then the overall state will look like this one. So unfortunately, this one looks very long, or yeah, to detect the single qubit error, we have to use 9 qubit, which is a little bit waste of the qubit. And then still the implementation of this kind of code can be implemented by this two stage, and then the first stage will the first stage corresponding to here will implement the um, this one, and then the next stage will extend each of the qubit to the 3 qubits. So it is a concatenation of the encoding scheme. So it is called as a um, concatenation of the code, and then the yeah. So this is so the when you hear about the sure code basically means that this 9 qubit code, and then again the capability of the sure code is that it can detect any arbitrary qubit error for single qubit error. And then you might wonder whether we really need all those 9 qubit, because it might sound a lot to just to represent single qubit. And then the answer is there is actually more complicated code which can reduce the number of the necessary qubit or necessary physical qubit. And then to fully develop such kind of theory, then yeah, it will be a waste of time if we have to start everything from the um, quantum information. So yeah, again, in this case, we borrow the all those well-defined theory in the classical information theory. So that's so yeah. In the next page, I will describe what does classical error correction code look like, and then how it can be adapted um, to the quantum information case. So the topic I'm going to discuss is called as something called as classical linear error correction code, and then you will see why it is called as a linear. And then in this case, we will also define that all the multiplication operation or any kind of plus operation will be done eventually in terms of the modular 2. So the only value we will have is either 0 or 1, and then the and I also want to point out that the bitwise addition modular 2 is equivalent to bitwise XOR. And then the another terminology we are going to use is something called as a code word, and then generator matrix, and then parity check matrix. And then yeah, let me explain what each of these means in this page and in the next page. So in the previous page, we were using the repetition code like 0, 0, 0, 0 will be mapped to 0, 0, 0, and the 1 will map to 1, 1, 1, and something called something like this one. And then if we think about what we really wanted to transmit, then the message we wanted to send is this part, but to deliver the information of either 0 or 1, what we used was the 000 or 111, and then we call these as a code word. So in other way, you can think that this code word, 3-bit code word, it can be not only 000 or 111, but it can be any other value, any other combination like a 010 or 100 or any kind of thing. But in this case, we just define only these two combinations as valid, and then all the others are invalid. And then in this case, we were the message, the type of message we want to deliver is only 0 or 1, so it can be considered as a 1-bit message. While in general, we might want to deliver many different combination of message. So in that case, yeah, let's say that we want to deliver one information out of 8 possibility, then we might the message might be 8 of them. Yeah. So in this case, it is a 3-bit message, and then for this case, we might use 8-bit or 10 bits or 100-bit, whatever value. So in that case, if I just say that 0001 bit represented by the code word of um, like 7, and then the 111 might be represented by another 7-bit and so forth. So each of them will have some corresponding bit or corresponding code word. And then in this case, these are using 7-bit. So in terms of the code word, we say that and this one is the 3-bit 3-bit code word. So in general, I will say that this number will, and then um, this number as um, k-bit message, and then I will say that the number of the bit used in the code word as n-bit. In this case, because we generally want to have longer code word compared to the message, so this will be generally hold. And then but you also can see that there is a lot of redundancy in terms of the code word, because all we want to represent is only the 2 to the k information, but to represent this small number of difference, we are using a much longer possibility, like 2 to the n. So in this case, we generally call this one as the nk code. And then specifically for this example, we are using 3-1 code. And if we generalize this situation or a little bit more, then we can say that what we are trying to do is we have a message space. So you can we can consider this one as some kind of vector space, and then I will call this one as a message space um, with k bit. Then we will have a vector space, and then inside there will be 2k vectors, and then each of the vector will be mapped to much larger code word space. So there will be code word space, and then sorry for the poor handwriting. And then yeah, this one will have the n-bit code word. So in this case, there might be the all the combination inside this vector is the 2 to the n vectors. However, only 2 to the k vector, this vector will be mapped to some vector, and then another, yeah, so there will be all the 2 to the k vectors, and then each of them will have some corresponding code word, but that does not necessarily mean that the uh, entire vectors in this code word will be consumed. There will be a lot of code, a lot of a lot of vectors which are not directly mapped from the message space. So again, this space is much larger compared to the message space. And then if we detect if we receive some word which does not belong to this set of the code word, then in principle we can say that we detected some error in the transmission. So yeah, in this general situation, and then you can see that this kind of mapping corresponds to some linear map. So we will call this mapping as a generator. And then for the simplest case like this one, we can say that our generator in that case was something like G, G is simply 111. And then in this case, what we can say is in for this one, yeah, we had the message of either only 0 or 1. So this is very simple, but if I just yeah, write down, then that means that this value will be 0, 0, 0. And then if I have a message of 1, then it will be mapped to the 111. So this is too simple, so maybe not interesting. But let's say that sometimes we want to deliver more than one bit of information, and then if we just use this same repetition code type, then this will be 0, 0, 0, 0, 0, 0, and then 0, 1 corresponds to 0, 0, 0, 1, 1, 1, and so forth, like this one. Oops. So this is a simple extension of the 3-bit repetition code or 3-1 code. And then now we are using 6-bit to represent 2-bit information. So maybe I can call this one as 62 code. And then in this case, the generator will be something like 111,000 and 000,111. And in this case, if I apply 00, then of course everything, yeah, this will be still multiplied like this one, and then everything will be just a 0. So 6 zeros like this, and then if we apply only yeah, if I use this one as 1, in that case, yeah, because then the they will these will multiply 0 times 1, 1 times 0, and plus 0 times 1. Yeah, so that will be 0. And then for the first 3 lines, it will be the same. And then for the first line up to the end, then it is 0 times 0 plus 1, 1 times 1. So we will have 1, 1, 1 like this one. So this generator matrix, in principle, can map all these code word, all these messages to the distinct code word. Yeah. So yeah, that's why it is called as a generator. And then the typical relation will be that if we have some message X, and then if we multiply a generator, then we will generate the code word like this relation. The concept of the parity check matrix is the extension of the parity checking circuit, which I showed you in the early part. And then the purpose of the parity check is if there is any error in the transmitted or received code word. So yeah, let me give you some more detailed example. By the way, let me use a different notation than the this one. Yeah, so yeah, previously I said I will call the message as an X, but yeah, let me call the message as Y, and then the code word generated code word as X, so that I can use this consistent notation for the parity check matrix. So yeah, let me consider some kind of simple parity check matrix, something like this. Like this one, and then let me call this one as H, which is the yeah, which represent the parity matrix. And then in this case, if what happens if I provide the correct code word, and then the code word we have is something like 0, 0, 0 or 1, 1, 1. And in this case, we know that because all the multiplication is 0, so it will be 0, and then the same with the 0. So with the correct code word, then we won't have any problem. And that's not only for the case of the 0, 0, 0, which is trivial, but even for when it is 1, 1, 1, the same situation happens. So if we multiply this row and this column, then 0 times 1 is 0, but 1 times 1 is 1, and another 1 times 1 is 1. And then the addition of 1 plus 1 is 2. However, because we are only considering the modular 2 addition, so in this case, the result is 0. And then similarly, for this case, yeah, because these two are 1 and these two are 1, so again, it might be 2, but because it is modular 2, so we again sorry obtain 0, 0, 0. So what this implies is that when we multiply the parity check matrix to the correct code word without any error, then we will get the 0, 0 value. Then what happens if I have some error in the transmission, like yeah, here? Now I know that there is a transmission error in the third bit, or yeah, maybe it is in the extreme case that the original code word was 0, 0, 0, but maybe two of them are flipped. But we are not considering that we will correct two values, or we won't allow the two bit flips. So we are simply assuming that there was single bit flip error. And then in this case, what happens if I just calculate the multiplication, calculate the matrix multiplication? Then it is 0, 1, which is 0, and then 1, 1, 1 times 1 is 1, and then it's just 0 again. So the value of this one will be 1. Then similarly, for this one, yeah, 1 and 0, 0, so it is 1. And then if when we have the error in the third bit, then we obtain a result like 1, 1. What about, so in this now, let's say that I have the 0, 0, 0, but there was a bit flip error in the first bit. In this case, if I calculate the multiplication, then this should be 0. And then now, 1, 1 survives. So you will have something like this one. So if I had the error in the first bit, then I will obtain 1, 0 value. Then what happens if I have the error in the middle bit? Then in this case, 0 times 1 is 0, 1 times 0 is 0, and then this is 1. And the second, for this case, 1 times 1, 1, and then 1 times 1, 1. So it will be 0. So in this case, if we have the error in the second bit, then we will obtain something like a 1, 0. And then if we convert this one in terms of the decimal number, then each of them represent the location of this error bit. So so what I can say is that if I multiply the parity check matrix on the correct code word. So if this was the correct code word, then it will be 0. However, let's say that I have some bit flip and then a bit flip error, and then let me write. So X represent one of these 0, 0, 0, 1, 1, 1 matrix column vector, and then error is because if you just do this addition with the modular 2, then this and then this might be something like a 1, 0, 0 or 0, 1, 0 or 0, 0, 1. Then it will actually flip it the non-zero row. So if I add this error column vector to the code word column vector, then the non-zero element will flip the corresponding corresponding bit. So this can represent the code word with some error. And then what happens if I multiply the this parity check matrix? Then in this case, because it is a linear multiplication, so the multiplication will be separated into two terms. But we know that because we are assuming the X is the correct code word, so this will be just to become 0. This term will become 0, and then we will just be left with this this result. So, and then as I showed you, the multiplication of the parity check matrix will identify which bit is error. So just by multiplying the parity check matrix to the entire received this entire received code, then we should be able to identify which bit is flipped. And then if we generalize, or if we compare this kind of idea to the linear algebra basics, then you probably already learned in the linear algebra class, we learned that when we are given some arbitrary matrix, we always try to find out x such that the multiplication of the matrix on this vector will produce the completely zero vector. And then unless typically we are not interested in the trivial case like all zero for the x value x vector. So even though the vector by itself is not zero, all zero, but the result of this multiplication becomes zero, and then we have the name for this kind of vector. It was called as do you remember? Yeah, it was called as null vector. And then the property, and then there are a lot of important properties related to null vector. And then one of the important property was that there might be more than one null vector, and then all those linear combination of those null vector can be another null vector. So that the vector space or space composed of all the null vector can be a very good linear space. So that's so, and then we call such kind of space as a null space. So and sometimes it was also called as a kernel of the given matrix. And then the so from the perspective of this linear algebra argument, then we can say that the good code word is actually the code word should live in the null space of the parity matrix. So that's the idea behind the behind all these linear error correction code. And then also what we can see is that the way we generate the code word from the message, then what we did was we generally multiply the generator, and we multiply the generator to the message, which is composed of a small number of bit, like a k bit, and then the and then we will generate this code word. But note that all the code word here are the linear combination of all these column vectors. So so we can claim that all the code word without any error are the linear combination of all these column vector. And then that means that if I call the one of the if this is a generator matrix, and then we can call each of the column as G1, G2, and G sub m. And then in principle, we know that if I just multiply the generator on the 1, 0, 0, 0 vector, the column vector message, then I will obtain the G1 column vector. And then if I multiply some 0, 1, whatever message, if I multiply the generator on the some arbitrary message, then this will be the combination of some column with another column and another column and so forth. So these are always the combination of these column vectors. So that means that if I multiply the parity check matrix on each of the not only the G sub 1 but any arbitrary column here, then they should always become 0. And then what that means is that even if I multiply the entire matrix on the parity check matrix, then because then the generator is composed of many different many columns. So eventually the multiplication will apply to each of the column individually, and then the we know that each of the column resulting column will be all zero. So we will eventually obtain a zero matrix. So that is the kind of relation between the parity check matrix and the generator. And then whenever you see the this relation like this one, then that means that if you multiply the parity check matrix to the generator, then the result should be zero. And another discussion we will have, and then when we are talking about the error correction code, another concept we have to consider is the something called as a Hamming distance. And the concept is actually relatively simple. If you remember about our encoding like this one, then the how many bits are different between these two codes? And then you see that these 3 bits are the same, while these 3 bits are the same. So there are 3 different bits, and then we call this number of different bits between two codes as the Hamming distance. So then what is the Hamming distance between this code and this code word and then this code word? All the bits are different. So the distance here is 6. Then what about the distance between these two codes? And then 3 bits are the same while the other 3 are different. So in this case, the Hamming distance is 3. What about the Hamming distance between these two code? Now it is 6. So that is the concept of the Hamming distance. Then the reason I'm starting to talk about the Hamming distance is what is the Hamming distance between the code word we were using in my example? So in my example, I was using the code word like 000 or 111, and then let's see what happens. What happens if I have any bit flip error in one of these bits? So 000, and then if I have the first bit is flipped, then it will be 100, and then if I have the second bit flipped, then I will have 010, and if I have the third bit flipped, then I will have the 001 bit. And then we can see that from this code word to go to this error code word with the error, then I had to change one of the bit. So in this case, I can say that the Hamming distance between these between this and this code word with one of these are 1. So this is the distance, and then for this case, I might have another the second bit might be also flipped, in which case it will become 110, and then of course this code word cannot be reached by only this path, but it can be also coming from this one. So in this case, from this 000 to 110, the Hamming distance is actually 2, because to go from here to here, then I have to go either this path or this path. And then if we keep applying this kind of concept, then I have from this word, I have the third bit also flipped like 011, or from here to here, let me use dashed line. Maybe I can. So from here to here, the second bit might be flipped, and I can continue to consider what kind of error I might have. Is then for this one, I might have the third bit flipped like here, and then there will be also the from here, yeah, zero, from here to here, yeah, the third bit might be flipped like this one, and then the second bit might be flipped this one, and so forth. So yeah, I can actually draw this kind of three-dimensional relation, and then as you can see, yeah, this one all look like the um, um, cube, and then the in this case, I can now ask what is the Hamming distance between 0, 0, 0 and then 1, 1, 1? And of course it is 3. And then but still, there is something we have to consider. For example, these three code words are only distance one, uh, distance one away from this code word. So yeah, I can collect, I can, and then if you receive one of these three, then you probably mapped or correct back to the 111, even though it might be coming from the 000 by distance 2 or 2-bit flips. But yeah, typical situation is that you will just correct these three. If you receive these three, then you have it will be higher probability that um, one of these three came from this 111 case. And then for these three cases, their distance from the 000 is only 1. So in this case, it is more reasonable to correct back to 000 if you receive one of these three. So that's where the Hamming distance is helpful. Yeah, and then if we generalize this kind of situation explanation, then we can even think about the situation like this case. Let's say that 000, and then this might come to something like 010 or 001, and then this might continue to change um, like this one. And then in this case, it can go like this one, or this can go like this, or they can also go like this one. And eventually, yeah, they can be also close to 111 case. And then from this diagram, it is obvious that it is better to map all the values to here, and then the similar argument, because of the similar argument, yeah, all of these code words should be mapped back to the 000 because of the um, distance. And then yeah, but there is still one more thing we have to consider, because here, yeah, these are all the possible combinations, so there is no other cases. But let's say that from this kind of diagram, yeah, there might be some other code words, yeah, which might be reached from 0, 0, 0, 0, or from 0, 0, 0 by only distance of 1. And then even from 111, yeah, there might be some the distance from 111 is also 1. Yeah, and then of course, yeah, there is no such kind of binary number here. But I'm just assume that there is some number. Yeah, when this diagram is extremely complicated, then there might be some cases. And then in this case, then the Hamming distance from here to here is not 3, because there is a path which has only distance of 2. And in this case, what is the most embarrassing part is, if I obtain this kind of code word, then to which one I should correct back to, and then it's not clear. So that's not a good that's not a desirable situation. And then so that's why we have to consider the shortest or closest distance, or yeah, probably yeah, I should say shortest distance between between any of the code words. So if I go back to the original discussion here, then when we map each of these message to the some of the code word inside this space, then inside this space, each of the code word, yeah, so if I have 10 code word mapped here, then we want to make sure that all the code words are separated from each other as far as possible. because let's say that all the code words are separated enough, like a distance of 10, but two of them are very close to each other, like only distance of 3. Then the problem is whenever you have any error, then there is still some chance that that error is caused between those two close code words. Then you cannot really correct all the situations. So that minimum distance between the valid code words are actually limiting the capability of the error correction code. And then if we say that yeah, for this times for this case, yeah, um, there is no such kind of thing like this one. So we can be safely say that the code the minimum distance between the two code word, which is 000 and then a valid code word, which is 000 and 111, it is always 3. And then in this case, yeah, I can say that this is can be represent generalized as a 2t times 2t plus 1. And then what this will imply is that we can always separate this code word space into two, or if we had more number of the valid code word, then at least we can separate all of those code word space into some kind of about, yeah, we can separate the entire space into the section or some region, and then within each region there is no ambiguity um, when you obtain some incorrect when you receive some incorrect code word, and then it will be always obvious which direction you should correct to. So in this case, what this really implies is that this t means that the number of the allowed error you can correct. So yeah, for this sense, for this case, because t is 1, so that what that means is that we can correct only 1 bit error. But if we have more than 1 bit error, then the problem is you might start from here, but because of the too many of error, you might end up here like end up like this place. And then in this case, there is no chance that you will correct this one back to here, because it will be more reasonable to correct this one to 111 rather than 000. So yeah, again, t basically means that the maximum number of the error bit you can correct, you can properly correct. And then the minimum distance, yeah, we will, if I write down it as a d, then yeah, in the previous case, when we are representing the code word in this way, but the more general notation is that we should also include that information. So we will say that nkd is the notation for the linear error correction code. So for our this simple example, we are using 3 bit to represent the 1 bit of information, and then in this case, the Hamming distance, the minimum Hamming distance between the code, all the valid code words is 3. So it is called as 313 code. So if we generalize what we had, what we discussed, or maybe I should say that if I give you some special example of the previous discussion, then one of the most popular code was called as the Hamming code, and then yeah the yeah, to explain all the generalization of the Hamming code will require some more time. And then because I'm already running out of time, so I will just briefly introduce that this is the shape of the Hamming code error parity check parity check matrix, and then there will be also corresponding generator which will be composed of and each of these column vector will be composed of the basis vector um, in the null space of this um, Hamming matrix, or the more generally it used to be called as parity check matrix. And then but the main reason I'm discussing about the Hamming code at this point is that the shape of this or the result of the Hamming code is directly related to what is called as the CSS code. And then the CSS means the Caldebank-Shor-Stein. And then, yeah, again, Shor is involved in this development. And then yeah, here I said that it is based on the Hamming code. And then if I just give you this kind of logical qubit 0 and the logical qubit 1, then you will be confused. Where does these results come from? So, but once you see the discussion of the Hamming code, then it will become more obvious. Then in the previous discussion, I derived this relation, and then we can use that relation. So if we consider that the relation between the parity check matrix and the generator matrix has this kind of relation, then we can think about taking the transpose of the entire equation. In that case, if I take the transpose of this one, then it will become T transpose multiplied by the H transpose equals still 0, which means that this one can be used as a new generator of the code word. And then in this case, yeah, this will become also the new parity check matrix for the this new generator. And then for the linear code, there is always a relation between the parity check matrix and the generator, and then there will be always correspond this transpose case, and this code is completely new code compared to this original G code, and then we call this relation as a dual code. And then the CSS code is basically made by using this concept. So for the new generator, yeah, let's say that we will note the this new generator as a G prime. Then what we have to do is just to transpose this entire matrix, which means that 0, 0, 1, 1, 0, 1, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1 matrix like this one. 1, 1, 1. Oh, sorry. 1, 1 case. And then in this case, from this one, now we can consider generating new code. So in this case, yeah, because now it is 7 by 3 matrix, so we can consider generating new dual code using this one as a new generator, and then we would obtain something like yeah, if I just have this case, then I will have everything will be 0, and then this first term here is obtained by just applying the 0, 0, 0. Then what about the second term? Yeah, let's say that what happens if I apply the 1 here, and then in this case, what I actually get is this column only, because all the other two terms are 0. So I will just have 1, 0, 1, 0, 1, 0, 1, which is exactly like this one. Then what about the third term? That was obtained by applying the 1, 0. So what I'm doing is 0, 0, 0 corresponds to 0, and then 0, 0, 1 corresponds to 1, and then now 0, 1, 0 corresponds to 2. So I'm just increasing these values from 0 to 7, and then if I keep increasing, then the result is now because now the second term is only non-zero, so we will obtain this column as the result here, 1 1. And then yeah, in this case, it is actually the sorry, not that one. Yeah. Yeah, so I obtain this one, yeah, which is the 0 1 1 0 0 1 1. And then what about the next term? Then the difference is this should be 1. And in this case, what I have to do is because these two columns should be added to each other, and then it is a modular 2 addition. So yeah, this is 1, and this is 1, and this is 0 0, this is 1, this is 1, and this is 0. And that's exactly what we have over here. So and then if you keep running, yes, from 0 0 0 to 1 1 1 case, then you will actually obtain all of these combinations. So again, the CSS code is basically developed based on the idea of the Hamming code, and that's why they might look very weird at first uh, sight, but and then it might take a while why they chose this dual code for the encryption of the logical 0 and 1 for the CSS code. But yeah, I hope that at least this give you some insight for the choice of the quantum error correction code. And then for the one case, the only difference between the 0 logical 0 and logical 1 is that it is basically adding 1 1 1 1 1 to each of the term over the for the 0 0 as 0 logical qubit. Then the adding 1 1 1 1 1 to the each of the term actually corresponds to flipping each of the value. So yeah, as you can see here, yeah, the corresponding term always have the flipped value like this one. So based on this one, yeah, I hope that you can actually understand that what kind of relation the 0 logical value and the 1 logical value has in terms of the CSS code. So in summary, this is the form of the CSS code, and then this is the definition of the logical 0 and logical 1, and then these basis vector basically came from the scheme of the 7-4 Hamming code. And then of course Hamming code is not only limited to 7-4, but it has a lot of it can actually increase a lot. And then along the same line, yeah, CSS code also use more qubits than 7 qubit. And but the reason we are for this case we are using 7 is basically based on the idea from the Hamming code. And then the this is kind of a minimum because this CSS the smallest CSS code can actually detect correct the bit flip error and then phase error. So yeah, instead of using 9 qubit, yeah, 7 is kind of a minimum number to be able to correct both types of error. And then the more discussion can be generalized by using the concept of the stabilizer code, which is also covered in the textbook of section 10.5. But but basically I'm running out of time for this class. So yeah, when I have some more time, then I can cover the stabilizer code. And I also want to point out that yeah, one of the important quantum error correction code is something called as surface code. And then this one is somehow optimized for the case when the qubits are arranged in this kind of 2D array shape, and then also when they have connectivity only when your qubits are connected to only the nearest neighborhood, like this one, and then there is no direct connection between from here to anywhere here, but they are only connected through these lattice shape, then the surface code is one of the optimal solution. And finally, yeah, this is this is the overview of the quantum computer architecture from my perspective. Yeah, of course, many of the idea also derived from other other presentation, but the point is there is no well-defined system architecture yet. And then the even depending on what kind of physical system you are using. For example, I'm using ion trap, but a lot of people also uses the superconductor, and also a lot of groups are using the quantum dot or the MV center or photons, and so each of them has its own physical advantage and then disadvantage. So based on those difference, yeah, you should design your quantum computer architecture along some different direction. So, but still, if we have to imagine some kind of generalized quantum computer architecture, then probably those architecture will have this kind of hierarchy. So yeah, maybe the first, the biggest separation will be the abstract quantum algorithm. Yeah, so up to previous, until we started to discuss about the um, quantum error correction, we basically assume that all the gates will be perfect. And then in that case, we can just, the goal or the job we have to do is develop the more efficient quantum algorithm. And you already learned that the quantum, to take advantage of the quantum computer, you need to actually design a good quantum algorithm, because in principle, yeah, quantum computer can simulate the classical computer probably in efficient way, because we know how to um, um, implement the NAND gate or some other universal gate for the digital logic. So in principle, you can re-implement everything in the quantum computer. However, if you really look at the real situation, then implementing the qubit or the um, each of the quantum operation takes much more effort compared to the digital logic. So there is no reason why we should use the quantum computer if you can um, if you can achieve your goal with a much easier way. So the quantum computer will be useful only when you have some problem which is not easy to solve with the classical computer. But if you can use some of the idea which was already described in the previous lectures, and then if you can come up with some good algorithm, then you can actually outperform the classical computer. And then this is the hardware level. So eventually what we have to do is control the physical system or physical device, and then to control these systems carefully or accurately, then you actually need to depend on the digital controller, and then we also need a lot of signal generators for each of the physical system. So this might be a hardware level, and then there is also a lot of things we need to do to optimize. And then, for example, I already showed you that the physical qubit will have a lot of errors. So to mitigate those errors, then we have to design the logical qubit or quantum error correction code. But the quantum error correction, the code which I showed you, like a source code or CSS code, they generally assume they have some kind of assumption for their design. And then for example, I assume that the amount of error for the for the bit flip error and then phase flip error will have the same probability, but there is no reason why they should be the same. So yeah, and then even for the binary symmetric channel, yeah, so there is no reason why the flip error will the probability for the flip error is the same for 0 and 1. Yeah, so there is no reason. So yeah, so depending on your given physical constraint, then you have to develop more optimal logical qubit scheme or the error correction code scheme. And then once you do that, then each of the logical qubit will be composed of a lot of physical qubit. So you have to also convert yeah, so yeah, up to here, the quantum algorithm will probably design at the level of the logical qubit, assuming that there is no error. But eventually, all of these circuit should be converted to the quantum circuit composed of the physical qubit. And then yeah, even for the same operation like a Hadamard gate, the way you implement the Hadamard gate is completely different between the photon or the any of the physical system. So yeah, you actually have to convert such kind of circuit to the actual sequence control sequence for your digital controller. And then once those and then only when you run those sequence on this digital controller, then you can obtain your you can reach achieve your goal. So this was sorry that the lecture is too long, and then I hope that you at least get some sense of the what does quantum error correction means.